Hello and welcome to another video. In this video, we're going to be doing the last problem of the weekly contest for this week, and it's apply operations to maximize frequency score. Now, I will preface this, I would strongly recommend doing the problem before this one in the contest because it's going to use the same exact idea of the median, and so I definitely strongly recommend that, and I'll link that one, and also I have another problem that I did that is similar to this. So definitely do those before this one. And so in this problem, you're given a zero index integer array nums and integer k. You can perform the following operation in an array at most k times. Choose an index and decrease or increase nums I by 1. The final score of the array is the frequency of the most frequent element in the array. Return the maximum score you can achieve. The frequency of an element is the number of occurrences of that element. So essentially what you want to do, the goal is you basically want to turn as many numbers as you can in this array into some number. And our goal is to figure out like what number that is and how many times we can do that. So here, essentially what they did is they turned everything into a 3 or into a 2. So they turned 1 into a 2, which took 1 operation. 2 is already a 2. They left 6 the same, and 4 into a 2, which took 4 operations. So we have 3 operations total, and we have 3 2s, so we should return, I think we return the score, right? Yeah, so we return 3. Okay. And in the next one, you can't do any operations at all. So you just want to return the most frequent element, which is 4. Okay. So like I said, this is going to be very similar to the last problem of the contest. So essentially, let's draw out some numbers and let's get some intuition into what we want to be turning our numbers into, first of all. So let's just say our numbers are just like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. And once again, just like in the last problem, we're going to get rid of this last index. And we're going to have this. So kind of here, let's say we have this. And let's just say we have unlimited operations. We don't have a k. We have unlimited operations. What's the number that we want to turn everything into? Ideally, right? Like we want to turn everything into some number. What should it be? And so here, kind of intuitively, you can probably figure out that you want to turn it into this middle number because that's going to give you the cheapest operations, right? So if we can definitely calculate it. Like let's say we turn everything into this. So we're turning everything into a 5, so it's going to be 4 operations, 3 operations, 2 operations, 1. And this is going to be 1, 2, 3, 4, right? And then altogether, this is going to be 20 operations. Now we can look to see what happens if we try some other numbers, like if we try bigger or smaller or so on. So let's see what happens maybe if we try to turn everything into a 4. So this would take 1 operation, 2, 3, and this would take 1, 2, 3, 4, 5. And this is going to be bigger. This is going to be 9, 12, 15. Yeah. And then this is going to be 21 now. So this is 21. Similarly, if you try to turn everything into a 6, it's going to be the same. And if you look at this little pattern over here, you can see that like as you move this will just be an increasing number that will be bigger, right? So instead of 1, 2, 3, 4, 5, if you make it go bigger from the middle, it'll be 1, 2, 3, 4, 5, 6, and then 1, 2, 1, 2, 3, 4, 6, 7, 1, and so on. And so this is going to keep increasing. So in this thing, you want to turn everything into the middle number. It's a little straightforward. Now let's see what happens, and let's get rid of some numbers. We don't need this many, so let's get rid of 2 of them. Let's see what happens. So like here, same kind of thing, right? You just want to turn everything to the middle number. It's kind of intuitive when it's all increasing by 1. But let's see what happens when our numbers aren't just like in a continuous increasing. Let's see what happens. So let's just say this is like 1, 2, 10, 20, 30, 40, 100 or something. Okay. Now that it's not symmetrical, right? So let's see what happens when we want to turn everything into. So it actually turns out that you do still want to turn everything into the middle number, and we can demonstrate that, and then we can get some reasoning for it. So if we turn everything into this, if we look how many operations that's going to be, it's going to be like 10, 20, 80. Maybe let's just use a smaller number because this really isn't going to matter. So let's just use like 50 here. Okay, so 30, and then this will be 10, and then this will be 18. Let's also use some easier numbers to calculate this with, right? So it doesn't get so annoying. So let's just say this is like 0, this is 5. That'll make it a little bit easier. Okay, so it's still not symmetrical. We're still achieving the same thing. It'll just be easier to add all these things up. So it'll be 15 and 20. And so our total here is 60, 90, 105. And if we actually try to do something else, and then we'll kind of get the intuition for why and how you could build this without having seen this before. So let's say we just try to go to the left, for example. Try to go to the left, we turn everything into a 10. So this will be 5, 10, 10, 20, 30, 40. So this will be 70, 100, and then this will be 115. And as you keep going left, it's going to increase once again. And if we try something to the right, like if we try this 30 instead, maybe, then what's going to happen here is it's going to be 10, 20, 10. Is that correct? Yeah. So 10, 20, 10, 20, 25, 30. There we go. Okay. So 55, 75, 85 plus 30, which is 115. So 115 again. So you do want to turn everything into the middle number, and here's how you could figure it out. So let's just say we start here. So the total distance away, like we pick this number. The total distance away here is, let's call it x, right? If we move right instead, like if we go from here to here, what's going to happen here is there were x numbers. So let's just use two variables, actually. Let's use two variables. X is how many numbers? And let's use y, the total like increase or decrease in value. Or let's just say like increase, something like that. Increase, decrease, something like that. So what's going to happen here is if you turn everything into a 5, all of these values, it's actually going to be all of these values. So if you turn everything into, let me go back to this. Okay, if you turn everything into a 5, the 5 will get closer, right? The 5 will get closer. All of these will actually get closer, right? Because these were all like whatever number away, right? Like each one of these, like this was 5 away, this was 10, this was 20, this was 30, this was 40, this was 50. If you turn these all into a 5, these will all get 5 closer. These 5 or 6 numbers, right? These 6 numbers will get 5 closer. So you're taking, we actually don't need this, I think. So basically what we're saying is we're going to take 6 numbers and we're going to make them 5 closer. So this is how many operations we will get rid of by turning it into a 5. Now, what did we lose? Well, now this 0 used to not take any operations. Now it is one number that will get 5 operations farther. So we add 1 times 5. So in total, we reduced our stuff by 25 operations. And let's get rid of this again. So we know that like 5 is better than 0. Well, what if we just keep going right? If we keep going right, and we can kind of like, you can kind of think of this recursively, every time you go right, figure out like what you're making more and what you're making less, and you're making them all more or less by the same value, right? Because if you're going away from a number, you figure out how much you went away, and then if you're going towards a number, it'll be the same thing, right? So if you go from 5 to 10, for example, then everything here will, when you want to figure out like how far you went more, it's just what number you go from to what number you go to. So because we increased by 5, all of these numbers will be 5 farther away, right? So if we go from 5 to 10, all of these numbers will be 5 farther away. There are 2 of them. And all of these numbers will be 5 closer, and there are 5 of them. So now we can just get rid of like this variable of how much closer and farther we got, and we can just think of just total numbers, because all of these numbers get, some constant variable times the number of numbers closer and farther. We can just figure out like if there are more numbers on one side, we always want to go there because we are decreasing the distance to a bunch more numbers, right? So it would basically be like there's some variable x that we are like adding or removing distance from, and then if there's more numbers on the right, it'll be like negative some number here, yx, and then the numbers that you're making, so these are the numbers you're getting closer to, and numbers getting farther away from would be like this. So if y is less than z, or sorry, if y is greater than z, then you're going to decrease your overall operations. And so that's basically how we can sum it up. We can just figure out like wherever or whatever number we choose to convert everything to, if we move it, how many things get closer and how many things get further. And if more things get closer, then we want to move it, right? Because they get closer and farther by the exact same number of operations. So yeah, to go from 5 to 10, 2 numbers would get farther and 5 numbers would get closer. So this is a beneficial operation, right? So we'd want to, now we realize we want to move to 10. So let's see what happens if we try to go from 10 to 20, for example. So if we go from 10 to 20, then these numbers will get further, so that's 3, and these numbers will get closer. So 3 get further, 4 get closer. So that's still better, right? Because more numbers get closer. And then if you try to go from 20 left or right, like let's say we go right, then these numbers all get further, and now these numbers get closer, right? 4 numbers get further, 3 get closer, same thing the other way. So that's how you determine it. That's how you figure out that, like, intuitively, that you always want the median in an odd array. Now, there's going to be something funny that happens in an even array, so let's do that as well. So let's just say we have this with an index of 7, and let's just make it 60. And I don't think I mentioned, but you are going to want to sort your numbers, because ideally when you want to convert every number into some number in some little chunk, you want to have the numbers as close to each other as possible, right? You don't want to the chunk you want to be converting wants to be numbers that are as close to each other as possible. Like if you have a bunch of numbers 1 through 100, you don't want to like have 198 and like 99 in the same array and try to convert them into the same number. You'd rather have 98, 99, and 100. So anyway, let's see what happens when we have this. So this is kind of a similar situation where, like, let's say we just pick this arbitrary location. This will have something. Now let's see what happens if we try to go from here to here. So here to here, we are making 3 numbers further away, and we are making 5 numbers closer. So this is a beneficial operation. So let's move it here. Now, let's see what happens if we try to go from here to here. So here, we are making 4 numbers further away, and we are making 4 numbers closer. So this is actually the same, right? We're making 4 further away and 4 closer. And if you did calculate this total, like to convert everything into a 20 or a 30, it will actually be exactly the same. And another fact is, let's actually do that. So let's actually calculate what it takes to convert everything into a 20, and then we'll see one other thing. And this isn't, I don't think it's relevant in this problem, but this is good to know for like other problems. So here, let's say we try to convert everything into a 20, for example. So this will be 10, 15, 20, 10, 20, 30, 40. So this is 70, 100, and then 130, 145. And another funny thing is, because we can convert everything into a 10 or we can use any one of these. We can pick anything in the middle, like that doesn't exist. Like let's say we try to turn everything into a 25 that doesn't exist. What would happen is all of these would get farther and all of these would get closer. So if you have, we can write that down as like all the things we found now. So for odd length, best number to convert into is median. Even length, any number between 2 middle numbers is equivalent to convert to. So anything from 20 to 30 is going to give you the same answer if you try to convert all of these. And the way you can think about it is, like, think about these numbers have a distance to the number you're trying to convert them, and how many numbers are on each side. And anytime you move your thing that you're converting to, you're getting closer to one range and you're getting further from another range. So as long as the number to the left and right is the same, then it doesn't really matter. And so that's kind of the idea. So we can use in here, any number 20 to 30 would give you the best answer. So now that we know that, now we basically need to figure out how to do this problem. And the way we need to do this problem is we're going to do a sliding window, and we're going to try to figure out, like, for the number that we're currently at, if we add it to the array, like if that's the right bound of our current array, then what's the most numbers we can include? And you might think this is tricky because like we have to grow and shrink our window, and that's kind of hard to like how do we always find the new median? How do we always keep track of like this total? And so I'm going to show you some tricks that you could do this in one time, so you can like have an array, add another number to it, and then calculate this total to convert using this kind of like median thing. And this is going to be really important to see what's going on. So let's actually take this window here. Let's just use these numbers, and we can just use this. Maybe let's change these numbers though, because this is not the best. So let's change some of these numbers, and then we'll make up like a k value and stuff. So let's say this is, let's see here. Let's make this like 1, 2. We could honestly just make it like 1, 2, 3, and so on, and that would kind of work. So, but let's do like 1, 2, 4, 6, 8, 10. It's like 15, 20 or something. See how this goes. And then let's say our k here is maybe like 4. Sure. Okay. So what we're going to keep track of is like our current array, right? Our current array, like a normal sliding window, and the number of operations we've taken, and our result, which is like the longest array possible. So our current array total, we're going to keep track of that. We're going to keep track of the result. And I'll just show like a blue line simulating the sliding window instead of the left and the right pointer. Do I have to do that? No, I guess I could actually just have like a left and a right pointer. It would be fine too. So we'll have 2 arrows simulating the left and the right pointer. And then we'll have a result. Okay, so initially, obviously, if you have one number, it doesn't cost you anything to convert it to itself, right? So that part's pretty straightforward. Like if you have 1, you just convert everything to 1. So we know we can have like an array of length 1. It's totally fine. And let me just double check what they actually ask. I think they ask you for like the longest, the frequency of the most frequent element. Okay, so essentially like we just say like, look, we can just have like a 1. Like we know that works for sure. And we're going to sort this array. So if this array had like a bunch of 1s, then we can obviously like add all those, and that'll be free, right? We can even do that in part of this problem. Maybe we'll change this number to like a 1 just to simulate it. And then we'll have a few duplicates. So let's say it's like 4, 4. Yeah, and then we can turn some of these into duplicates. And then, so we'll have something like this. Then we'll have like 6, 10, 12, 14 or something. It's good enough. Okay, so obviously this is going to work, and it's going to be 0 operations. Now when we add the next number, what we really are figuring out, and we need kind of like a universal thing that will work for duplicates as well. And so the idea is our current array is this, and our median is this value, and it's an odd length array. But this is actually going to work really easy, but this is going to be good to explain why this works and really understand it. So we're going to move our right pointer over here. And what's going to happen here, let me actually move these values as well over here. And we're basically going to check like what was the cost of inserting this 1. Well, our old median was 1. So we know like the cost of our old array. And actually, notice our median doesn't change for this array. So if we had an odd length array with a median, we can use that same median for an even array, and you'll kind of see how this works as it gets bigger. So our old median was this value. When we insert this, the median can still be this value here, right? Because in an even length array, any one of these left or right medians works. So when we insert a value, what we really have to say is how much more does it cost? And when we insert a value, it's basically going to be value minus the median that we had, right? Because essentially we're turning everything into that median. So in this case, our old median was 1. So if we're inserting 1, it costs us nothing. So this is fine. And now we update our result to length 2 array. Now we move this in. Now, remember our old median was this. But when we move this in, we actually have to shift our median to this, right? Because our median has to be, for an odd length array, it has to be the middle one. But if our median was this for this array, remember that for an even array, we can actually pick one of both of the middle medians, and the cost to turn everything into that array is the same. So for this array, even though our median was this, we can also say our median was also this, and it's the same cost, right? Because it's an even array, so either one of those is the same. So we're basically going to say, and I'm going to show this as an arrow. So we're going to say, okay, our median was actually this now instead of this, because it's the same for an even array. So we can use that. So we can say like our old median was this. And so now when we add the 4, it's just going to be the old array with this median, which we have a cost for. Plus, we just added a 4 and we have we're keeping the old median. And how much does it cost to turn a 4 into a 1? Well, that costs 3. So we're going to turn this 3. And this is still a valid window, so we can move on. Now, for this median, this was our old median, and for this 4, we can still use that, right? Because it can be any one of the left or right ones, and it's going to be exactly the same, right? So we're gonna use this still. Actually, if we add a 4, yeah. So actually, I don't think we are. Yeah. I think we are not. We're not going to use this median over here. We're actually going to shift it to this median. Actually, no. We are going to use this median. Yeah, we have to because we can't shift it to this median yet. We will shift this median in the next part. So yeah, when we add this 4, we actually do have to we do have to use this old median because we can't shift it to this median because the median of the old array has to be this number here. It can't be this one, right? Because it has to be the middle one. So this will be the median, and then we basically have to figure out, okay, to add this 4, we know this old array had a count of 3. So now to add this 4, we know the old one. So now how much does it cost to turn this 4 into the old median, which is 3. So now our cost is 6, which is too big. Maybe let's make, just for interesting, a more interesting solution, maybe let's make k a little bit bigger because these numbers are kind of far apart. So let's actually make k, I think let's just make k 6. Yeah, that'll be fine. So, and notice this would work, right? Basically what would happen is you would turn these 4s into 1s. So this array would be cost 6. Okay. And now this is a valid array, and this is length 4, right? When we added this 4, the array was length 3, and then we added this 4, this array is length 4. Okay, so now we keep going. But before we do, notice that now, when we add this 6, in order to add the 6, this has to be the median. And now that our array is actually an even length, now we could shift our median for free because the value of converting everything with this median, the value of converting everything into 1, is the same as converting it into 4. And it is, right? Because if we convert everything into 1, we're converting the 4s into 1s, which will cost us 6. But we can also just convert the 1s into 4s, which will cost us 6 as well. So we're using this property where if you have 2 medians, if you have an even array, any one of them is fine. So we're essentially shifting our median, and now we can go to the 6. And now when we add the 6, it's gonna be added to the array of the same exact median, right? The median of this whole array is the same as this array. It's going to be this middle number. So once again, we have to figure out, like, okay, to add the 6, all we really need to do is change the 6 into a 4. That's going to cost us 2 operations. And so now we have 8 operations. And so that makes sense. So now essentially what you do to get rid of things from the left is kind of the same idea as adding to the right. When you get rid of a number, you're basically turning this array into this array. And notice this array and this array have the same valid median we can use, right? Like this array, it has to be this middle one, and this array can be one of these. So we'll just say, okay, let's stick with this one. And to get rid of the 1, all we're really getting back is however much it took to turn the 1 into a 4. So how much did it take to turn a 1 into a 4? That took 3 operations. So now this is 5. Right? So because we had too much of a cost, our cost was too big. So now we can move this up here. And now our cost is valid again, and our median is one of these two, right? But because we're going to be adding a number in the future, we want our median to be over here again, because when we add this number, we want this array, right? So for this array, the median can be one of these two, doesn't matter which one. So we'll just say, let's use the right one. And this is going to be a lot less easier in the code because we're actually just going to calculate the median on the fly instead of like moving this bottom arrow. So we'll just say when we're adding from the right, if there are, like, let's say we're adding this number from the right and the array is something like this, then we can easily figure out like what's the middle index. And if there are 2 middle indices, we'll always take the right middle index because we have to, right? So like, let's say we get to this number here, we'll always take the right one because the previous, actually, let me think about that. Yeah. We will always take the right one if it's even now. Yeah. And so that's what we're going to do. So let's just keep going here. So what's going to happen here is we will add this 5, right? And remember, this is going to be at the same location as here. Yeah. I think the reason more why we have to, basically we're going to take when we have two medians, when we add from the right, we're going to take the right one, and when we remove from the left, we're going to remove the left one, and it basically works out, like the math works out. But this is kind of the idea behind that, is you can move your medians around. So let's say we add 10 now, and remember this array had the exact same median as this array, because it can be either one. So when we add 10, really what we're asking is how much does it take to convert this 10 into a 4, because that's what we're going to be using. That's going to take 6 operations, so we have 11 total here, and this is too big. So because it's too big, we need to remove from the left. So if we remove from the left, we need to remove this 1, and when we remove the 1, essentially what we're going to do is, yeah, we're going to remove the 1. So, and we have to remove the 1 using this like left medium here. So we're going to get 3 operations back. And we can just double check where we're at just to make sure I did the math correctly for everything. But let's see. So if we remove the 1, we're going to move this over here. And our medium is here. So let's just see what this is going to be. So, and like I said, turning everything to a 4 or a 6 is going to be exactly the same, right? In a array length 4, but let's see what happens here. So we should have a total of 6 and 8 operations. Yeah, we just turn everything into a 4. This is our current array, and that's actually correct. So this is perfectly correct. Okay, and now let's keep going. So remember, when we add this value, we want to use this median, right? Because, yeah, we want to use this median because we're going to be turning everything into a 6. Because we have to, right? Because like, and also notice here, turning everything into a 6 would cost the same as turning everything into a 4, because this would be 4, 6, 8. So yeah, when we have this 12, we want to turn everything into a 6. So we were going to move our median, and because we can, because we have an even array, so we're going to move our median over here. And now we're going to go to this number, and we're going to add it, and we're going to see how much does that cost. So, oh, by the way, I actually forgot one more thing. So this is still 8, so it's still too big. So we still need to actually remove before we do this, right? We still have to remove one of these. And so what we actually have to remove is we're going to remove, like our new median has to be here when we remove this, right? So we're going to use this median to remove. So when we remove this, we're going to get back 2 operations. So we can move this arrow over. Move this arrow over and get back 2 operations. So now we have 6. And that is valid, right? And you can check because this is 2 and this is 4. So now we actually have a valid window. And now we can keep going. And now that this was odd, now when we add this number, we can just reuse this, right? Because we had to reuse this because we want our median to be the same when we add our new item. So I know, kind of confusing, and there's a lot here, but yeah. So essentially now we add this 12, and that's just this distance here, because we can just turn everything into a 6. So that's going to be 12. And in fact, you can do that, right? It'll be 2 plus 4 plus 6, so it'll be 12 total. So now this is too big again, so we have to start removing. And so when we start removing, we are going to remove, we have to remove from the right, I believe, because, yeah, we have to remove from the right because our new median is going to be 10. So we can get back a bunch of operations here. And so this is going to be like this. So we remove this 4 from the right, we get back 6 operations because our new median is this. So we can get rid of this. So essentially, when you remove from this side, you're going to want to compare to the right median, and when you add to this side, you're going to want to compare to the left median. Because when you add things here, like let's say this is even, if this was this, now it's this, you're reusing the left median, not the right median. So that's why it would work like that. Okay. And now here we have a total of, we're turning everything into a 10. So this is going to be 4 plus 6, or 4 plus 2, which is going to be 6, which is fine. So we can keep going. So we can add this item over here now and use this median of 10. So now we can move that. And this is going to take 4 more operations. So this is going to be 10. Double check one more time. So if we turn everything into 10, it's going to be 4, 6, 10, which is correct. So now this is too big, and we have to remove from the left. Remember, when we remove from the left, we are going to pick the right median, because when we remove this number, our array is going to turn to this. So we want to pick the right median. So this is how much we're getting back. So we're getting back 6. So now we have a total cost of 4, and this is over here. And now we're out of bounds. And so the biggest window we found was length 4. I think it was like this one. But that's kind of how you do it. So we can write that down. So we can say sort numbers, sliding window, when we add a number, just figure out what was old median, and what we need to add is a number minus old median. Then to remove a number, we get back old median minus that number, right? So we're adding to the right, removing to the left, and we can do this in O of one time, where we're basically, anytime we remove something, we can just figure out like what was the median, and we can just figure out how many operations we're getting back. And that's basically it. So now we can code it up. Okay, and then one more thing to clarify quickly before we do the code is, like I said, when we just clear up a little bit of confusion, because I think my old code had indexing in a little bit different way. But yeah, essentially when we add a number, so let's say we're adding this number, this is the new right number we're adding to this window, we are always going to pick the left out of the two mediums, right? So any one of these is fine, but we're going to want to pick this one because this was the old one of the original array. So that's always going to happen. And if it's odd, then it's going to work out fine with the math we have. So if we add like this number to this window, then it's going to be fine because it has to be this one. It has to be it has to be this one. And we're gonna do that in the code. And same thing, removing. So if you're removing from this array here, if you're removing an odd number, then you're always going to be removing, because you're turning your array from this into this, you're always going to be removing this number here. And if it's even and you're removing a number, so if you're removing for something like this, then what's going to happen here is you're turning your array from this into this, and so you're always going to be removing this number here. And that's kind of the idea, is we can shift mediums for free, because anytime we have an even length number, like any one of those works, and that's kind of the idea behind this problem. Okay, now we can code it up. So essentially, we're going to have result, and we can just set it equal to 1, because obviously, like, one number is always going to be valid. You can set it equal to 0 as well; it doesn't really matter. We're going to have a left, and we're going to have a cur, which is going to be like our current total. We're going to sort our numbers, and we're going to do a sliding window. So for every single right we add, essentially the index we want is nums right minus nums right plus left over 2. Because, like, let's say we are at, let's say our array is like at index 0, 1, 2, 3, and we just added index 3. We want our median to be index 1, which is going to work out like that, right? So it's going to be 3 plus 0 over 2, floor divided 2, which is going to be 1. And if this was, if we went from even to odd, then we always want to take the leftmost medium, I believe. Let me check that, actually. If we went from even to odd, no. We always want to take the rightmost medium. Yeah. If we go from even to odd, we always want to take the rightmost medium, because this medium is going to be the same for this whole thing, right? So if we go from even to odd, we want to take the rightmost medium, and if we go from odd to even, then we want to take whatever the medium was of the old number that was in the middle. Yeah, so this will be fine. Okay, so this will give us that. We also need to do this. And yeah, and you can, if it's still a little bit confusing, I would draw out the values and just realize that, like, anytime your number is even, you can use either one. Anytime your number is odd, you have to use this one here. And so that's the medium that you have to use, right? So if you go from even to odd, then in your even number, you could have used either one, but in your odd number, you have to have a specific one. And if you go from odd to even, then you have to use the median that was the middle of the odd number. And so now what basically we have to say is while cur is greater than k, right? Well, if we have too many operations, we're going to be subtracting from the left. And so when we're subtracting from the left, like I said, it's going to be the reverse. So when there are two mediums here, we are actually taking the leftmost medium, but instead from the left, you're going to want to take the rightmost medium. And like I said, you can draw this out as well and look at the picture. So this is going to be actually this thing divided by 2, and then we need the ceiling at this time. And that'll give us the rightmost medium, or it will give us the middle one. Okay. And so this is going to be the medium, and we have to subtract by numzel, and that's how much we get back. So this is how much we get back. We just subtract from curd to see how many operations we get back. And we move the left up one. Now we do just the basic sliding window length, right? So result equals max result right minus length plus 1, right minus left plus 1, and we return result. But yeah, I think this problem is kind of tricky to figure out how to like do this whole medium shifting in O1. But I think once you draw out the pictures and realize like when you have two mediums, you can pick either one, and when you have one medium, you have to pick one. And knowing the whole like the optimal number to change everything into is a medium, then it makes it a lot more straightforward. And it does kind of help that problem 3 use the same exact concept. So let's take a look, and you can see it's very efficient. Yeah, most of this stuff is like a lot slower. So because I think there's like other ways to do this with like prefix sums and like binary search and stuff, but that's going to be slower because it basically that's like a true n log n, where for every single index you will actually binary search. Well, here we just do a normal sort. So that one would have been like n log n times like a bunch. So here, the time is n log n because of the sort. And the space is O1 because we don't have anything. So I don't think it's too hard of a problem, and this is kind of a cool trick. And honestly, that's why I do think it helps for these hard contest problems. Like even if you can't do them, watch solutions and learn to understand them, because I feel like in almost every single one, I've kind of learned like a new trick or two that I can apply to other problems. So hopefully this is helpful, and if it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.